Have you ever wondered what it takes to build, assemble, test, and maintain aircraft trusted to carry millions safely through the skies? When a massive power transformer must reach a distant power plant within weeks instead of months, ordinary transport is no longer an option. This video documents an extraordinary logistics mission led by UTC Overseas to move a giant Croatian-built transformer from Zagreb, Croatia, to the Philippines aboard the world's largest cargo aircraft, the Antonov AN-225. The operation begins after the aircraft's distinctive nose is raised, revealing an enormous cargo compartment measuring 6.4 meters wide, 4.4 meters high, and 43.35 meters long, with an internal volume of 1,300 cubic meters. Built in 1988 to carry the Soviet Buran space shuttle, the Antonov AN-225 Mriya, meaning dream in Ukrainian, remains the largest and fastest aircraft ever designed for oversized cargo. With an 84-meter fuselage, an 88.4-meter wingspan, and a maximum takeoff weight of 640 tons, it is the ideal solution for urgent, heavy-lift transportation. UTC Overseas selected the AN-225 to transport a 318 MVA power transformer manufactured in Zagreb for the San Lorenzo power plant in the Philippines. Since the plant could not deliver electricity to the grid without the transformer, rapid delivery became critical. While sea transport would normally require 40 to 45 days, the airlift dramatically reduced the shipping time, helping the manufacturer fulfill an accelerated delivery schedule. The transformer, weighing nearly 140 tons, is first moved from the factory to Zagreb Airport using a specialized 12+12 axle transporter with push-pull trucks. The entire convoy stretches approximately 90 meters, weighs nearly 400 tons, and completes the journey in about 3.5 hours under carefully coordinated road conditions. Upon arrival at the airport, engineers begin the highly precise loading operation. The transformer is lifted into a specially designed steel transport frame that distributes its immense weight across the aircraft floor. After being securely mounted inside the frame, the entire assembly is carefully winched into the cargo hold and restrained with approximately 120 steel tie-down ropes. Every movement is performed only a few inches at a time while cranes, aircraft specialists, and logistics engineers work in perfect coordination. Although deteriorating weather creates additional challenges, the loading continues safely throughout the day until late evening, when the transformer is finally secured inside the Antonov AN-225, completing one of the most remarkable heavy airlift logistics operations ever witnessed. The ultimate load wing test of the Airbus A350XWB is a critical structural certification process designed to verify the strength and safety of the aircraft's wings. During the test, hydraulic actuators gradually apply increasing upward forces to the wings, simulating extreme aerodynamic loads far beyond those experienced in normal flight. As the load rises, the wings bend dramatically, demonstrating their flexibility and composite material performance. The test continues until the wing reaches its ultimate load limit, confirming that the structure can withstand maximum stress without catastrophic failure, ensuring safety, durability, and compliance with aviation regulations. The automated manufacturing process for large aircraft CFRP structures begins with preparation of a 5-meter diameter rear pressure bulkhead tool designed for double curved geometry layup of dry carbon fiber textiles, including structural plies and reinforcing patches. Long structural plies are automatically unwound from material rolls and placed by a robotic effector that rolls the textile directly onto the mold surface, ensuring accurate draping across the complex curvature. Epoxy resin is applied during fixation to stabilize the initial ply layers and eliminate the need for additional adhesive materials. Reinforcing patches are automatically cut by a CNC cutting system, then lifted by a robotic gripper and transferred onto a movable transport table before entering a robotic cell. Inside the cell, a modular gripper identifies the geometry and exact position of each cut piece using integrated recognition systems. The patch is then picked by up to 127 suction modules, which adapt their configuration to the target geometry during transfer. As the system moves toward the tool, the modules dynamically reshape the patch to match the double curvature, ensuring controlled draping and accurate fiber orientation. Optical sensors embedded in the gripper continuously monitor the quality of deformation and placement. Once the target position is reached, the patch is pressed onto the tool surface and fixed in place. Inspection systems, including fiber angle cameras and laser sensors, verify edge accuracy and draping quality. Long structural plies can also be applied using two cooperating robots whose end effectors are adjusted to the target geometry. First, the system measures the current position of each module and calculates the required configuration. Both robots then grip the long cut piece at opposite ends and pre-drape it over the mold. An autonomous algorithm computes a collision-free trajectory and synchronizes the motion of both robots toward the target position. During placement, the ply is pressed and draped precisely onto the curved tool surface. In parallel, a multi-kinematic gripper automatically picks stringers, which serve as stiffening elements. After reorientation, the stringers are placed at precise locations on the preform. Vacuum grippers on adjustable manipulator arms ensure secure handling of each component. Each stringer position is individually configured to match structural design requirements. Epoxy resin is then applied to fix auxiliary material packages. Based on a digital twin model, human-robot interaction is coordinated for loading auxiliary materials. The robotic cell is pre-configured with safety constraints and collision-free paths that are simulated offline. Manual loading of auxiliary components allows a final quality check before automated placement. Synchronized motion of manipulator arms ensures accurate and non-invasive positioning of each material package. All auxiliary materials are successfully placed according to the target geometry. A semi-permeable membrane for vacuum infusion is then positioned using a mechanized system and sealed around the entire perimeter. The membrane is compacted in narrow regions using a multi-kinematic gripper, applying controlled pressure normal to the tool surface. Finally, the preform is prepared for resin infusion and curing, completing the automated CFRP manufacturing cycle. A vacuum bagging system ensures airtight sealing of the entire assembly prior to injection. The resin infusion process introduces epoxy resin uniformly through the dry carbon fiber stack, enabling complete wetting of all layers. Controlled flow conditions ensure consistent distribution of resin across the complex geometry of the structure. After infusion, the component is cured under regulated temperature and pressure cycles. This curing stage solidifies the composite matrix and achieves final structural integrity. Throughout the entire sequence, automated monitoring systems continuously verify fiber orientation, layer placement, and process stability, ensuring consistent quality in each manufactured aircraft structure. Additional inline sensing units embedded in robotic end effectors provide real-time feedback for adaptive control of ply deformation and placement accuracy, reducing deviation during high-precision layup operations. The integrated system coordinates robotic motion paths and material handling strategies to maintain continuous production flow while minimizing defects and ensuring repeatable aerospace-grade quality in real time across complex CFRP structures in automated manufacturing environments worldwide. From testing philosophy to production, the Boeing 747-8 program demonstrates how safety validation, engineering discipline, and large-scale industrial coordination define the creation of one of the most complex machines ever built. Before full production is allowed to continue, the aircraft must survive a series of extreme tests designed to push every system beyond normal operational limits. One of the most demanding procedures is the rejected takeoff test. During this test, the 747-8 accelerates down the runway at near takeoff speed before the pilots apply maximum braking force. The brakes absorb enormous energy, causing them to glow red from heat. Fire crews are positioned nearby, not to intervene, but to observe and verify that temperatures remain within acceptable limits. If fire or structural failure were to occur, the aircraft would immediately fail certification. This test proves that the aircraft can abort a takeoff safely and still allow passengers to evacuate. Boeing expects this to be the only rejected takeoff the aircraft will ever experience, but demonstrating this capability is mandatory. Only after passing such tests can the aircraft proceed confidently through the remaining stages of production and assembly. The 747-8 is the most modern evolution of the jumbo jet. It is the longest commercial aircraft ever built and the most efficient in its category. Like all previous 747 models, it is manufactured in Everett, Washington, inside Boeing's enormous assembly plant north of Seattle. This megafactory is the largest building in the world by volume. Its doors form the largest mural ever recorded, and the interior space is so vast that clouds have occasionally been observed forming near the ceiling, 11 stories above the factory floor. Inside this vast structure, the factory operates like a self-contained city. It has its own fire department, internal transportation system, and several of the busiest cafeterias in the region. Workers use bicycles and tricycles to move between work zones, and even experienced employees can take months to learn the layout. Despite the apparent chaos of aircraft parts scattered across the floor, every operation follows a carefully planned sequence. Each aircraft occupies a dedicated assembly position, and every task is performed according to a strict schedule. For nearly 4 decades, the Boeing 747 was the undisputed king of the skies. That reign ended when the Airbus A380 surpassed it in size and passenger capacity. With 2 full passenger decks and seating for more than 550 people, the A380 addressed the rapid growth in global air travel. However, airlines were no longer looking only for size. Rising fuel prices and environmental concerns made efficiency the most critical requirement. The older 747 became expensive to operate and less competitive. Rather than abandoning its flagship aircraft, Boeing chose to reinvent it. Designing a completely new airplane would have required more than a decade and billions of dollars. Instead, Boeing decided to radically redesign the existing 747 platform, transforming it into a more efficient and environmentally responsible aircraft. The result was the 747-8, capable of flying faster, traveling up to one-third of the way around the world without refueling, and burning less fuel per seat than any previous 747. Although the Airbus A380 remains larger, the 747-8 consumes less fuel per passenger, an important factor for airlines making long-term fleet decisions. To achieve these improvements, Boeing relied on technologies already proven on the 787 Dreamliner, including advanced aerodynamics, modern engines, and digital flight control systems. The Everett facility functions primarily as a final assembly center. Components arrive from every corner of the world. Passenger seats come from Germany, wing structures from China, and flaps from Australia. A single 747-8 requires more than 6 million individual parts, and every one of them must arrive at exactly the right time. Boeing uses a just-in-time production system to minimize inventory costs. Parts are delivered only when they are needed, reducing storage requirements and capital investment. However, this system leaves little margin for error. Any disruption can delay the entire production line. To prevent interruptions, Boeing ensures that critical components never run out. The most valuable of these are the engines. Each engine costs approximately $20 million, making it impractical to store them for long periods. Engines are installed only 1 or 2 days before the aircraft leaves the factory, arriving precisely on schedule. Every component, from massive structural sections to small tools and fasteners, is electronically tracked. A single missing bolt could cause a disaster if it entered an engine or fuel tank, so quality control is uncompromising. Production begins with the wings, the most important aerodynamic components of the aircraft. The wing assembly area occupies nearly a quarter of the space dedicated to the 747 program. The wings of the 747-8 are the largest Boeing has ever built. Each wing is large enough to support 4 average-sized houses on its surface. Internally, each wing consists of 3 main spars running along its length, connected by 55 ribs. This structure provides the strength needed to support the aircraft's full weight during flight, turbulence, and landing. Each wing must also safely carry up to 58 tons of fuel. Aluminum skin panels are attached to the structure using thousands of rivets. Every rivet is critical. Workers install each one carefully and then return to inspect them again. Errors at this stage could cost lives, so every fastener is treated as a safety-critical item. As the wing takes shape, its aerodynamic profile becomes clear. Earlier versions of the 747 used wing designs based on 1960s technology. The 747-8 adopts advanced aerodynamic concepts derived from the 787 Dreamliner, increasing lift while reducing drag. During flight, air flowing over the wing creates low pressure above and higher pressure below, generating lift. At the wingtips, however, air from the lower surface curls upward, forming vortices that increase drag. To reduce this effect, the 747-8 features raked wingtips angled upward. These wingtips push vortices farther from the wing surface, reducing resistance and improving fuel efficiency. However, flight tests revealed a new challenge. Engineers detected a small vibration in the wings known as flutter. In certain conditions, the wings oscillated by up to 5 centimeters. In extreme cases, uncontrolled flutter could cause structural failure. Rather than redesigning the wing, engineers applied a modern solution. The aircraft's fly-by-wire system uses computers to interpret pilot inputs and control flight surfaces electronically. Sensors detect vibrations, and the computer makes small, rapid adjustments to counteract oscillations. This system actively damps flutter during flight, maintaining stability even at the edges of the flight envelope. While the wings are assembled, work continues on the fuselage. The fuselage is built in multiple large sections, including the nose, the central section with the distinctive hump, and the rear section. Each section is assembled panel by panel and covered with green protective vinyl to prevent damage. The lower fuselage is built upside down to allow easier access. Once complete, it is rotated 180 degrees using specialized equipment. A single fuselage section is so heavy that it requires a crane capable of lifting 34 tons. 26 cranes operate on more than 50 kilometers of tracks throughout the factory, transporting sections between stations. Before any section is moved into its final position, workers carefully inspect it to ensure that no tools or loose parts remain inside. Joining the fuselage sections and wings is one of the most complex operations in the entire process. This stage is usually performed at night, when fewer people are present and the risk of error is reduced. Alignment tolerances are measured in millimeters. First, the forward fuselage section is positioned to receive the wings. The wings occupy nearly the entire width of the factory floor, leaving only a few centimeters of clearance between the wing tips and the walls. Two tractors pull the wings at exactly the same speed to prevent lateral movement. Once the wings are secured, the rear fuselage section is attached. As the sections come together, the unmistakable silhouette of the jumbo jet finally emerges. The completed airframe measures 76 meters in length and 68 meters in wingspan. Thousands of workers contribute to this moment, coordinating their efforts with precision developed over decades. After structural assembly, attention turns to the engines. The 747-8 uses 4 advanced General Electric engines, the most efficient ever built for this aircraft. Earlier 747 engines consumed more than 12,000 liters of fuel per hour. The new engines burn significantly less while producing greater thrust. Composite materials reduce engine weight by 180 kilograms each, allowing increased payload or passenger capacity. The engines are also the quietest ever installed on a 747. Installing each engine is a delicate operation. Concrete blocks are placed inside the fuselage to prevent the aircraft from tipping backward. Each engine weighs 7 tons and must be aligned precisely. Only 8 bolts secure each engine, tightened to exact torque values. The front mounts are designed to break away safely in the event of a severe failure, allowing the engine to separate without damaging the wing. With engines installed, technicians begin testing the aircraft's electrical systems. The 747-8 contains enough wiring to supply power to more than 50 houses, with kilometers of cables running throughout the airframe. All systems converge in the electronic bay, which functions as the aircraft's nervous system. The fly-by-wire system is not fully automated. Pilots command the aircraft, and computers interpret those commands. Multiple layers of redundancy ensure that if one system fails, others can take over. Interior completion follows. The 747-8 interior draws inspiration from the Dreamliner, featuring improved lighting, modern colors, and increased comfort. Each airline customizes the interior according to its own branding. Before painting, the protective vinyl is removed. A base coat is applied by hand, followed by multiple layers of paint. Weight is carefully controlled, as excess paint increases fuel consumption. A typical paint job uses about 500 kilograms of paint. Before delivery, the aircraft undergoes extensive flight testing. Test pilots push the aircraft beyond normal limits, performing extreme maneuvers. Load distribution tests use water ballast pumped through barrels to simulate different cargo and passenger configurations. Minimum takeoff speed tests deliberately scrape the tail on the runway using a protective block to ensure safe rotation. PI Castings is a leading specialist in the manufacture of high-integrity investment castings with over 65 years of experience in the industry. Based in Altrincham, Cheshire, the company operates a fully integrated casting and machining facility capable of producing both ferrous and non-ferrous components. As one of the few companies in Europe with the capability to deliver high-integrity castings and rapid prototypes from a single production site, PI Castings serves a wide range of industries, including aerospace, defense, nuclear power, inert gas transport, mechanical equipment, and general engineering. The company utilizes advanced manufacturing technologies to support both conventional production and rapid prototyping. Using CAD data provided by customers, PI Castings can produce components without the need for tooling by applying 3D printing methods such as thermojet printing, stereolithography, selective laser sintering, and quick cast systems. This enables fast and accurate development of complex parts in both aluminum and steel materials. The investment casting process begins with the creation of a precise wax pattern, which is produced by injecting wax into a die. These wax patterns are then assembled onto a feeder system to form a casting tree. The assembly is repeatedly dipped into high-grade ceramic slurry using robotic systems. While the coating is still wet, ceramic particles are applied to build up a strong shell layer. This coating process is repeated several times until the required shell thickness is achieved. Once dried, the wax is removed in a steam autoclave using the lost wax process, and the ceramic molds are fired at temperatures above 1000 degrees C to increase strength and eliminate residual wax. Molten metal is then poured into the preheated molds, allowing it to flow into thin and complex sections. After cooling, the ceramic shell is broken away, and the castings are separated from the feeder system. Final operations include fettling, blasting, heat treatment, machining, and quality inspection. The company employs strict quality control procedures using advanced testing methods such as radiography, dye-penetrant inspection, magnetic particle inspection, metallography, and 3D coordinate measurement. With ISO 9001, AS 9100, and other certifications, PI Castings ensures high precision, full traceability, and reliable delivery for demanding industrial applications. Saudi Arabia has witnessed the rise of advanced aircraft services, Al Salam Aerospace Industries, as a global leader in heavy maintenance, overhaul, and modification of aircraft. The company has established itself as a trusted provider of comprehensive maintenance solutions for both commercial and military aviation sectors. Al Salam Aerospace Industries is certified as an approved maintenance, repair, and overhaul MRO center under the Saudi Civil Aviation Authority, the United States Federal Aviation Administration, and several international aviation authorities. It also holds global ISO quality certifications, reflecting its commitment to the highest standards of safety, performance, and reliability. Since its establishment, the company has focused on understanding customer requirements and delivering tailored solutions, especially for military aviation. Its first major contract with the Royal Saudi Air Force in 1993 marked the beginning of a long journey of success. In 1997, Al-Salam entered the military overhaul sector with the Tornado aircraft program, followed by the AWACS and Aerial Refueling Aircraft program in 2000, and the F-15 program in 2001, which continues to this day. In addition to military services, the company began commercial and private aircraft maintenance in 1993, building a strong regional and international reputation. It provides services for Boeing, Airbus, and Bell helicopters, offering heavy maintenance, systems upgrades, avionics modernization, corrosion control, and engineering support. Al-Salam Aerospace Industries also specializes in aircraft interior refurbishment, designing and executing luxury cabin modifications for private jets. Furthermore, the company invests heavily in training Saudi talent, developing engineers and technicians to support national self-sufficiency in aviation maintenance. Future plans include establishing a dedicated aviation maintenance academy. With modern facilities including 3 large hangars capable of accommodating Boeing 747 aircraft, specialized F-15 maintenance hangars, and advanced workshops, Al-Salam continues to expand its capabilities. The company remains committed to innovation, growth, and contributing to Saudi Arabia's economic development as the preferred choice in aircraft maintenance, overhaul, and modification. The video captures a complex heavy lifting operation in which 2 large cranes work in perfect coordination to lift the fuselage of a Boeing 707 aircraft from a heavy transport trailer and position it onto its designated installation site on the ground. The scene begins with the aircraft fuselage securely strapped to a specialized multi-axle trailer designed for oversized cargo. Ground crews carefully inspect all rigging points, ensuring that slings and lifting beams are properly aligned to distribute the massive load evenly. Once the cranes begin hoisting, the fuselage slowly rises from the trailer in a controlled vertical motion. Operators in both crane cabins communicate constantly to synchronize every movement and prevent any imbalance or sudden shift. The aircraft body gradually clears the transport platform, while rigging tension is continuously monitored for safety. As the lift progresses, ground technicians guide the fuselage using taglines to maintain stability against wind and minor oscillations. The 2 cranes carefully maneuver the long cylindrical structure through the air, ensuring it remains level at all times. Slowly it is lowered toward the prepared installation foundation, where precision alignment marks have been preset for accurate placement. Final adjustments are made millimeter by millimeter as the cranes ease the fuselage into its exact position on the supports, completing the delicate and highly coordinated operation safely and efficiently. After the load is fully settled, rigging teams gradually release tension from the lifting slings while maintaining full control of the suspended structure until stability is confirmed by supervisors on site, ensuring a safe and complete installation of the aircraft fuselage into its final position.